quickly let's start the session because today's session is going to be like a little lengthy. I will try to finish it up in 2 hours, but probably I might have to take additional time. There are close to 80 slides today, 76, 77 slides are there. Okay, and this is our last session on fluid mechanics. Quickly say hello to your class teachers. We have Anil sir and Anshul sir as your class teachers. We don't want to have an extra class during the Diwali phase, so that is why I want to finish this chapter today. I feel and I hope that you guys also want the same, right? Otherwise, in the Diwali week, we will be having our extra class. Thank you, Samapita. Okay. Okay, so we'll speak at the end of the class. You guys have a lot of questions to ask other than the academics, as always. So you can ask me at the end of the class. You all know that we can always speak after the academic part of the discussion is done. Okay, everyone, shall we start? Please write class 1 in the chat box if everyone is ready. Can see me, can hear me, have their notebooks ready with pen. Great, awesome, very good, super. So as always, I'll be switching off the chat. We'll start straight away today's discussion, and we are already in the discussion of real fluids. Last time what we spoke about is one of the properties which is related with real fluids, and that's what we call as the property of viscosity. Okay, so viscosity is something that we understood is basically the property because of which the liquids, when they travel in the form of layers, a layer will try to create a friction force on the other layer. So that is what the property is, just like the friction property. Viscosity is the friction in fluids. Then we spoke about the volume flow rate formula called as the Poiseuille's formula, okay, which is talking about the amount of volume flowing per unit time is through a pipe in which we have created a pressure difference. That pressure difference is P. The radius of the tube is R. The length of the tube is L, and the fluid which is flowing has viscosity eta. So pi r to the power 4 pressure difference upon 8 eta L, where eta is the coefficient of viscosity, right? Whose units are Pascal into seconds and the Poiseuille's also. Okay. Then we talked about the friction force or the viscous drag force which acts on the solid body when it is placed inside a fluid and tries to move. It came out to be 6 pi eta RV, which what is important is that it is directly proportional to the velocity. So we understood that the more fast a body tries to move inside a solid body in a liquid, just a minute, right? Sounds like my AC just died. Anyway, so more fast a solid body will try to move in a fluid, more the resistance that it will experience from the fluid itself. Okay, and as the force is directly proportional to velocity, and if we speak about a say spherical body which is falling in a viscous fluid, mg is acting, buoyant force will be acting on it, and this viscous force will also be acting on it, viscous drag. And this force will keep on increasing till the time the total upward force becomes equal to mg, and then comes the situation when F net acting on the body becomes 0 and the body achieves a constant velocity, which we call as the terminal velocity. Formula also we found 2r square g by 9 eta, rho s minus rho l. Rho s is basically the density of the body, rho l is the density of the fluid in which this body is trying to travel. Okay, so as we have a lot of things to cover today, that's why we do not have any recap questions to solve today. Rather, we directly jump to today's agenda. These are the 4 topics that we'll be covering today. First one is called as the topic of surface tension. Okay, that is primarily the discussion today, surface tension. We'll speak about why surface tension comes into existence because of cohesion and adhesion. We'll speak about cohesive and adhesive forces. Then we'll speak about the energy which is associated with surface tension called as surface energy. Okay, obviously it's a surface phenomena. Then we'll speak about the additional pressure or excess pressure inside a drop or a bubble. And finally, we'll speak about the angle of contact and more importantly, capillary action. Okay, so everyone, let's start. We'll speak about the types of forces to eventually talk about the property of surface tension. Okay, so all of you must have seen, I don't know if you guys ever tried to do this experiment or not. If you will take older generation shaving blades, you guys might have seen those older generation shaving blades. If you will try to gently place it on the surface of water, in the flat position, you will be able to place it on water. Even if it is very sharp, it will be able to float. But if you place it like this, if you place it vertically, it will cut through and will go inside, right? Similarly, so many insects we have seen who you will feel as if they are actually walking on the water surface. So the surface of certain fluids, they behave like they have a surface covered with an imaginary or invisible kind of membrane. Okay. Yes. So this membrane is basically due to the property which we call as surface tension. Okay. Yeah, razor, not exactly razor blade, the earlier razor blade I was talking about. Okay. In fact, a needle, a very small sewing needle, जो कपड़े सिलने के काम आने वाली जो needle होती है, that needle can also be placed very gently on the surface of water and it will not sink. Okay. Cool. Yes. So everyone will be walking towards that part. But to understand surface tension, we need to understand the 2 types of forces which we call as the adhesive forces and the cohesive forces. The first one is what we call as adhesive forces. These are basically the forces which are attractive forces acting between molecules of different materials. Okay. Like when we put our hand inside water, the water touches our hands and eventually some droplets get stuck to our hands. So the force which is acting between water droplets and our surface as in our skin is basically an adhesive force. How do I remember it? I see that adhesive sounds like different. Okay, AD, adhesive, has a sound like different. So adhesive will be between different molecules or different type of materials. Okay. When we speak about the other type of forces which are called as cohesive forces are basically the intermolecular forces which are acting inside the same type of materials. So say water molecules are applying force on each other. If we are speaking about say this liquid, this is iced tea or any type of tea or any liquid for that matter, the forces which are acting between 2 molecules of same substance, same material will be known as the cohesive forces. Okay. Now what happens when we speak about a fluid? When we speak about a fluid which is filled inside a container, okay, a real fluid obviously. When we talk about any molecule of that fluid inside the bulk means inside the volume of the liquid. That liquid is, as the entire fluid is stationary, that molecule is also stationary. And the net force acting on it due to all the molecules of similar nature effectively must be cancelled out. That is why the net force acting on that molecule is 0 and it is stationary. But when we look at the situation of the surface molecules, they are experiencing the attractive cohesive forces because of the molecules which are below them. The lower layers are definitely applying a force downward on them, but there is no molecule of a similar nature on the top of them. So because of that, these surface molecules, only when we speak about the surface molecules, they do not have the net force acting on them to be equal to 0. In fact, if you will try to work out the resultant, you will find out that the net force is acting on them in the downward direction. So because of these forces which are acting on all the molecules of the surface of the liquid, it basically looks like, or it is explained to be like a stretched membrane. When we speak about a membrane, I'll give you a very good visualization of that in the next slide. But right now, just imagine it to be like a piece of cloth, a very thin, invisible piece of cloth. That's how the surface tries to behave. And this property of this surface feeling like it is stretched so that things can be placed on it also at times is known as the property of surface tension. So what exactly surface tension, everyone? Surface tension is basically the net cohesive forces which are acting in the downward direction on any surface. Surface tension is the property because of which this happens. Okay, everyone. So how do we visualize it first of all? Have you guys ever seen any percussion instrument like a drum or a tabla or dholak maybe? Have you guys seen? the surface of that, where they beat it to make the sound, right? That surface is actually stretched, right? That surface is actually stretched. So liquid also can be imagined. You have to just to visualize it, okay? Just to visualize it, the surface of that percussion instrument is how you can visualize the surface of a fluid, okay? So that stretching is basically because of the surface tension. Okay, everyone is able to understand, able to relate an image in their mind, right? Okay, no, not today. I'm in a very serious mood. I want to finish it off in time. Okay, so no time pass. Okay, everybody. So how do we define surface tension? If we take any imaginary line on the liquid surface, now try to imagine it like a, imagine it like a surface of a tabla or any percussion instrument, an imaginary line. This is that line, okay, imaginary line. So this line is under the tension force from both the sides because you are pulling it on both the sides. So the force which is acting per unit length of this line is what we define as the surface tension. This is how it is defined. The force of surface tension is perpendicular to the line considered on surface and tangential to the surface. That means what? If this is that surface, the surface tension is going to act tangential to it. You're going to stretch it in this manner. So the surface tension will be trying to apply the force which is acting tangential to the surface. And how do you calculate it? At times surface tension will be represented as S. Okay, let me tell you this here only. At times you'll find it represented by capital S or capital T also. But remember, depending upon the chapter that you are talking here, this is the fluids chapter happening. So capital T cannot be the tension force of string because in the entire unit of fluid mechanics there is no discussion of a rope or a chain or a thread. So if capital T is used in this chapter, it cannot be tension. It is surface tension. Tension was a force. Surface tension is not force. Surface tension is force per unit length. Look at the units of surface tension, everyone. Okay, for your simplicity, we will use or we will write the formula of surface tension or expression or a symbol as S only. We will not write it as capital T. I'll try my best because I am habitual of writing it as capital T only, but I'll try my best. Okay, everyone. So it is Newton per meter which we define as the units, and dimensions becomes M L0 T minus 2. So please remember this, that surface tension is defined to be the force acting per unit length. Okay. Yeah. Good. So let's have a look at some example. First, we have understood the feel of it. That is more important. That it's basically the property because of which the fluid surface behaves like a stretched membrane. Okay. So an example, all of you guys. Soap helps cleaning in clothes. Why? We all know that with the help of soaps and detergent, we are able to clean the clothes very easily. The options are, it says that chemicals of soap changes. It increases the surface tension of the solution. It absorbs the dirt. It lowers the surface tension of the solution. So the correct answer is actually option D. What happens when we add soap or detergent in water? Basically, they try to create adhesive bonds with the dirt molecules, the detergent molecule. There are two things that they do. First thing, what they do, the little bit of chemistry comes into picture here, surface chemistry. So the soap molecules, or you can say the detergent molecules, they have affinity. They are more, they have affinity towards the dirt molecules. The dirt molecules will be sticking to them, so it becomes easier to clean them out. Secondly, they also reduce the surface tension of the solution. Okay, that means liquid will not try to stretch itself more. It will try to give away the dirt molecules. So soap will get stuck to the dust particle, and the grease molecules, maybe any liquidy or any sticky molecule also, and can be removed by the action of water itself. So this is one very trivial question that I want you people to remember, that whenever we add soap or any detergent in water, it lowers the surface tension of water and gets sticks to the dirt molecules. Okay. Now this one is going to be a quiz. Please read the question. Meanwhile, I'll try to create a quiz out of it. Okay. So what the question says is, the spiders and insects move and run about on the surface of water without sinking, because the options: elastic membrane is formed on water due to property of surface tension. Spider and insects are lighter. Spider and insects swim on water. Spider and insects experience upthrust. So giving you all 15 seconds for this here, and the time starts in 3, 2, and 1. Should be easy for everyone to do an answer. Okay, I'm guessing everyone got this right. Let's see. Very nice, very good. Yes, so they are able to do it not because of their own self. It is basically because of the fluid property, and that is property of surface tension. It behaves like an elastic membrane. Great. So one example for all of you. This is from JEE 2020. It says that a small spherical droplet of density D is floating exactly half immersed in the liquid of density rho. So we have a spherical ball which is inside the fluid, half of its volume and half of it is outside. The liquid density is rho. Surface tension is D. The radius of droplet is going to be how much is what we are interested in finding. So everyone, have a look at this. If you look at the solid body, the small spherical droplet. Okay. So what is happening? Mg is acting downward. The buoyancy force is acting upward, and the surface tension force is acting on the circumference of it. Okay. Just a second. Yeah. So if you look at this ball, if half of it is inside the liquid, okay, if half of it is inside the liquid, going full screen, all of you. So half of it, okay, I do not know, it's very bright right now. So what is happening? The boundary of it, where it is in contact with the solid, with the liquid, this portion is inside. Okay, this portion is inside the liquid. So the equator part of it, you can imagine it like an equator part of it. The equator is forming a ring. The equator is forming a ring where the surface is coming in contact with the liquid. The surface of it is forming a ring where the liquid surface is coming in contact here. Okay, so when we try to write down the forces here, what is happening here, guys? Mg is acting downward, buoyant force is acting upward, and surface tension force is always going to try to stretch the liquid surface. So it is trying to stretch the liquid and trying to bring the entire liquid on it. So in this case, guys, we can say that Mg will be balanced by the force applied because of surface tension and the buoyancy force. So already we know how to write down Mg. Mg is going to be density into volume into G, right? And that density is given to us as small d. Okay, small d is the density of the solid body. So d into v into g. This d is not differentiation, d is the density. Please don't get, don't misunderstand this part. Keep that in mind. Okay. Second thing, on the right hand side, because half of the volume is only immersed, so when I write the buoyant force, it is rho liquid into the volume submerged, that is v by 2 into g. So we are so far so clear with that. And the force, we know that surface tension is force upon length. So how much length of this liquid is coming in contact, or how much of the circumference is acting as the length of the part of the liquid which is coming in contact? So we say that the length is equal to the circumference of that equator part. So 2 into pi into r. 2 pi r is the length of the circumference multiplied by capital T, where capital T is, my dear friends, surface tension. I told you that at times you might find it written as surface tension as capital T. So please don't take capital T as the force. It is the surface tension written over here. So I can write volume 4 by 3 pi r cube. V by 2 becomes 2 by 3 pi r cube. If you simplify this to find out the value of r, first of all, 1r gets cancelled. This part will be brought here. And when you try to simplify this, the value will come out to be 3t upon 2d minus rho into g. Okay. If you want, we can simplify it also. Let's take it on the next slide and simplify it quickly. Okay. So from here, first of all, we can cancel out this 2. Remains 2 here. Apart from that, I cancel 3, and I multiply 3 here. And I will cancel one more r, but I will write it as d into, pi also got cancelled. So pi got cancelled. I have r square into g equal to, and multiplied by 2 also, 2d into r square g equal to, pi got cancelled, rho r square into g plus pi got cancelled, r got cancelled, 3t is what we are left with. We have cancelled pi also. Okay, and one r got also cancelled. 1 3 got multiplied on the right hand side. So take this here. You have 2d minus rho r square g equal to 3t. So r square comes out to be 3t upon 2d minus rho. So r will be equal to 3t upon 2d minus rho in under root. That is what is the answer, 3t, 2d minus rho. Okay, and one g was also there in the denominator. Okay, everyone? So that's what comes out to be the answer to this question. Okay. So more importantly, so far we are just getting into the field of understanding of surface tension. We have understood that surface tension is making sure that the surface of any fluid which is exposed to any other medium, that is where the surface molecules are experiencing different forces. Because of that, the surface is behaving like a membrane which is stretched by the property of surface tension, and the property value of the surface tension is force per unit length of that given surface. Okay. Now, moving on to more important discussion, that is about the surface energy. So what exactly is the surface energy? Surface energy is nothing but, again, it is basically right now your membrane is under some kind of instability. It is basically storing some energy. So surface energy is basically the potential energy that is contained by the molecules of the liquid surface, and due to which they will stay on the surface against inward forces of the attraction by the other molecule. That means what? Because these molecules are unstably being placed on the top, they are not allowed to go inside. So they are basically storing some kind of energy as the potential energy, and that energy is what we call as the that potential energy is what we call as the surface energy. So this energy is basically possessed by the liquid surface molecules only. Okay. So if we try to calculate the value of this, say we take an example here. You guys all must have done this while we take, especially in our childhood when we take shower and when we are, rubbing soap on our hand. If you will just open up your hand like this, you will find a soap film being formed here, right? So similarly, if you create a soap film with the help of a U-shaped, maybe a rail and a movable rod over here, this is very lightweight, and say you have a soap film being created over here. So how do we know that surface tension force is going to work? This ring, if you will leave it here, or this rod, if you will leave it here, and soap film is formed, the surface of any fluid will always try to reduce its potential energy, or anything in this universe will try to reduce its potential energy. So in that case, to reduce the surface energy, to reduce the potential energy, the surface area should be reduced. So by nature, any fluid will try to reduce its surface area. So if you will leave the system as it is, this movable rod will be pulled left side because of the force of surface tension. This is the force due to surface tension. Okay, so that means what? If you apply an external force on the right hand side, you are basically spending some energy because you will be working against the force of surface tension. So that work which will be done by you to elongate the entire surface film by a distance x, that energy that you will be spending will get stored in the form of potential energy. This we know from the chapter of work by energy, that whenever an external force is working, and whenever you are working against any other force which is present in the situation, you will definitely have to overcome that work. You will have to put your energy at stake, and that energy will get converted in the form of the potential energy of that system. So that is what appears in the form of the surface energy of a film. One thing that I want you people to always remember, that whenever we are going to calculate the surface energy, there will be two types of situations. One situation where you will be dealing with conditions where liquid drops are involved. There are two possibilities in general that you deal with. One will be a drop kind of situation, means you will try to calculate the surface energy of a droplet or a water drop. So water drop will only have one free surface. One free surface means surface which is in contact with air. Okay, so there will be only one surface in that case. But then there are possibilities of bubbles, second case, bubbles or films. The diagram that you see right now, a soap film or a soap bubble. These two things will always have two free surfaces. Soap bubble has outside also air, inside also air. So we consider there are two surfaces in case of a bubble. Similarly, in the surface which is given in front of you right now, the soap film, it has two surfaces. One that is on the other side of the screen, one is on this side of the screen. So have a look, guys. When we try to calculate the amount of force which is acting, we will not write only F into D. D is the length of this thing. Okay. Force per unit length is what we are calling as the surface tension, right? So when we write the value of the force, just a second, when we try to calculate the value of the force due to surface tension, we will say that force is going to be surface tension into the value of the length. So S into D is going to be the value of that force. But here, because there are two surfaces, that is why we will be multiplying it by 2 also. Okay? In this case, because there are two surfaces, that's why. Okay? So S into 2D is going to give me the value of the force that is internally developed because of surface tension. Now, because I am applying a force from outside, and the minimum force that I need to apply is to counterbalance the amount of force which is existing inside due to surface tension. So whatever work that I am doing, I am going to apply the same amount of force F. Okay? This force can be variable if I keep on changing the value of the amount of surface area. So say I displace the rod, this rod, if I displace it by a distance x, then the amount of work that I'll be doing will be F into x. What is this force? Force is S into 2D multiplied by the value of x. This 2 into D into x. What is D into x? This is the amount by which you have moved it, and this is basically the length of that rod. So D into x is basically the area of one of the surfaces. The other surface is also there. That is why the total surface area is 2 into D into x. Right, everyone? D is not differentiation value. D is basically the length of that film. X is the amount by which you have elongated it. So S into A. What does S into A mean? S is basically the surface tension. A is the value of the area that by which you have increased it. So in short, this work is going to get converted into the form of the potential energy, which we are calling as the surface energy. So in very simple words, everybody, surface energy is nothing but the product of surface tension with the amount of surface area. So at a given area, what is the amount of surface energy which is stored in a surface? First of all, check how many surfaces are there to write down the value of total area. Okay, multiply that total area with the value of the surface tension. That is what is the surface energy. So other way is to calculate the value of surface tension. So far we have defined it to be force per unit length. We can also calculate it by surface energy per unit area. Okay, I've written that same important points over here. That remember that bubble has two surfaces and a liquid drop will always have only one surface. Okay, everybody please note down this formula or keep this in mind. That surface energy is surface tension multiplied by the total surface area. When we say total surface area, number of surfaces are important. Okay, good enough. So one more way of defining surface tension is surface energy per unit area, apart from force per unit length. Also, surface tension is the characteristic of a surface of liquid due to which it tries to decrease its area. Okay, and for this purpose, it applies the force of attraction between the molecules of the surface. Okay, so I was actually looking for a video that I personally did around 4 or 5 years back. I recorded it also, but it was in my older phone, which I have obviously no idea where exactly now that phone is and where the videos of that is. What I did in that, to prove that surface tension always tries to reduce the surface area of a film or any fluid. You guys can try doing this experiment. Okay, I'll see if I can find anything on YouTube for that. Okay, surface tension. Mostly I'll find. Just a second, everybody. I don't want it to just remain a theory part. I want something which is easily understandable to be done with the help of experiment. You can try doing this experiment at your home with your own home setup also. Okay, everyone. So guys, sharing my screen so that you guys can see this. Okay. Can you all see the screen? देख सकते हो चलो तो ये वाला एक्सपेरिमेंट फटाफट से देखते हैं stop writing anything in the chat box I've kept the chat on but I want you to focus on the screen okay so this is liquid soap and this is a frame if you don't have a frame you don't have to worry about it you can take any bangle मम्मी के पास बहुत सारे बैंगल्स होंगे पतली वाली कोई भी बैंगल चूड़ी लेना और उसको लेके भी you can dip it in a soap solution soap का quantity अच्छा रखना keep quantity of the soap good and dip that bangle inside and dip it in such a way that you are able to pull it off easily okay see how this fellow is going to do this see how what this fellow is doing taking this frame putting it in the soap solution picking it up now you all will be able to see that a soap film has been formed there. Audio is not important. Now see what he's going to do. He has taken a thread, which is actually a loop. Means what? That thread is not a long thread. The thread has been connected. Both the ends of the thread are basically connected. And randomly he's going to place it. He or she's going to place it on the soap film. Have a look. Placed, randomly placed. Soap film is there. That's why. And now everyone. Now see what that person is going to do. Right now on both the sides the same fluid is there. So same surface tension is acting on both the sides of it. We will be pricking the interior part of this loop. This loop you see. We will be pricking. We will be puncturing this central part of it. And because the film is the liquid film and due to surface tension it will try to get the minimum area, it will try to achieve minimum area. So what will happen, the moment you will puncture it, this loop will try to acquire the maximum possible area that it can, which is basically a circle. And see, this is happening. Okay, so see what is going to happen now. See, immediately after that was done, I'll play it in ultra slow motion so that you all can see this happening. See, we'll be puncturing it and it will immediately convert into a circle, into a loop. Anytime now. Okay, and here it happens. See, immediately converts into a ring. Outside this thread now, you have the soap film, which is trying to minimize its area. That's why given the maximum area to the thread. This is because of the property of surface tension. Okay, everyone? Hope you guys understand the experiment. You guys can try doing it and see soap film is still not breaking by itself. That's how it's done. I think he's doing it one more time. Or with two loops he's trying to do, I guess. Okay, single loop, only bigger loop he has taken. Okay, everybody? Okay, so you guys, I did this experiment myself, recorded it also, but so I don't know where that video is now. So fortunately we found something here. Right. Okay. You guys can try doing this. Okay. Chalo, everyone. So this is what the surface tension property tries to do. Surface tension is the characteristic of surface of liquid due to which it tries to decrease the area, and for this purpose it applies the force of attraction between the molecules of the surface. Somebody was asking for the formula slide. This is the formula slide. Yeah, simply surface tension into area is the surface energy. Okay. So we'll understand it better by looking at some examples. First example, the raindrops are in spherical shape due to. Take a guess. Why raindrops do you think will be spherical or are spherical in shape? The surface tries to have the minimum possible area, and this is something that you will learn later on in mathematics when you study calculus. It will try to minimize the surface area, and out of all the 3D surfaces, spheres have the minimum surface area. Okay, so that is why the property, the surface tension, it tries to minimize the surface area and the possible shape is going to become spherical for a raindrop. Okay, now this one, it is actually a quiz, but I'm not giving it as a quiz because this is a question which you guys have not seen yet. So I'll first try to show you how it is done. This question says that energy needed to break up a drop of radius r into n number of drops of radii small r. So one big drop, you want to break it down into small r radius drop, n number of such drops. So this is capital R, this is small r, and these are n number of drops. So we can say that the volume will definitely remain the same. So 4 by 3 pi capital R cube will be n times 4 by 3 pi small r cube. So r is definitely n to the power 1 by 3 r. This is what it is. Okay, everyone. Question is asking us the energy needed will be how much. So everyone, can I say that when one drop converts into n number of drops, those n number of drops, their total area will be more than the single drop, right? The total number of that means the total surface area is increased. So if total surface area is increased, can I say that the energy is also increased? Surface energy also increased. And obviously, if I'm breaking something into multiple pieces, I'm doing some work, I'm losing my own energy. So that gets stored in the form of the energy here. So if I want to calculate the amount of work done, that's basically the amount of surface energy changed. That means the total energy of n drops minus the energy of one drop. Is that clear? The energy of n number of drops minus the energy of one drop. And how do I calculate the energy? Multiply the surface tension, say capital T, with the surface area, which is 4 pi r square. So we will just write down A. And because it is drop, how many number of surfaces do I take into account? One or two? For a drop, how many surfaces will I take into account? Only one. Remember. Okay. If same question happens for a bubble converted into bubbles, then you will take two surfaces into account. Okay. So n into 4 pi r square into capital T minus 4 pi r square into small t. So because the options are in terms of small r and capital R both, we can actually convert capital R into small r or small r in terms of capital R also. That is not needed here. So simply n into 4 pi r square is the area multiplied by the surface tension of n number of drops, and 4 pi r square into capital T is the surface energy of bigger drop. 4 pi t taken common, 4 pi t into n r square minus capital R square. Very simply, that's what becomes the answer to the question. Okay, everyone, what we have done, please remember the logic behind it. That whatever is the energy which has changed, surface energy, is the result because of the work which is done by the external agent. Okay, so based upon this, let's see if you guys can try a few questions from here. Question on the screen: the radius of a soap bubble is increased from 1 by under root pi. Okay, this is basically the earlier radius, 1 by root pi. centimeters to 2 by root pi centimeters. So if the surface tension of water is 30 dynes per centimeters, then the work done will be, already CGS units are the options. So you don't have to convert anything into SI unit. All I can tell you that work done is going to be the change in surface energy of this soap bubble. But when you're writing the energy, make sure that this 2 is taken into account because bubble has two surfaces. Okay, so 2 into T into A, T is the surface tension, A is the surface area. For a bubble, surface area is 4 pi r square. Giving you all complete 2 minutes, take your time. Go easy on it. Don't make mistake. Try to go slow but steady and accurate. Your time for 2 minutes starts in 3, 2, and 1. It actually does not require 2 minutes. Question is not even worth 1 minute, but I'm sure you'll be able to do it correctly. So utilize. Thirty seconds more. Come on, people. Okay, we are in the countdown. And let's see. Okay, and overall, so yeah, the work done has to be the change in this energy. So 2 will remain. Surface tension is not changing. It's only area that is changing, right? So area final minus area initial, and obviously because you're increasing the radius, you're increasing the area also. So 2 into T into 4 pi R2 square minus R1 square. That's what it is. So 8 into pi into T, that is 30 into 2 by root pi square. So when square that value, you will have 4 by pi minus 1 by pi. Simplify this value, get the answer. So when we simplify this, guys, 8 pi T, putting up everything, this comes out to be pi get cancelled. 3 3s are 9, 9 8 are 72, 720 ergs. As simple as that is the answer, right? So option C is the correct answer here. Okay. So one more. It says that 1,000 small water drops of equal radii combine to form a big drop. The ratio of final surface energy to the total initial surface energy of 1,000 drops. Surface energy of 1 drops to the surface energy of n drops. Giving you this time only 90 seconds, and the time starts in 3, 2, and 1. Come on, people, you can do it. Energy is surface tension into the area. Surface tension is not changing because the liquid remains the same. Okay, half time is gone, 45 seconds more. Last 15 now, everyone. Okay, and the time is up. Let's see. So can I say that energy of big to energy of small drops, when I'm going to write that down, okay, the ratio of final energy to the total initial energy. So when we speak about the energy, it is the surface tension into the surface area, that is 4 pi r square of the bigger drop, and surface tension into 4 pi small r square, but there are such 1,000 drops available, right? So that means it is capital R square by 1,000 into small r square. Also, when we write the volume, 4 by 3 pi r cube is going to be 1,000 times 4 by 3 pi r cube. Means for a smaller drop, whatever was the volume, such 1,000 drops combined to give one single drop. So this gives me r cube equal to 1,000 times r cube. That means r is equal to 10 times r. So we'll put this here. That means 10 r square is 100 r square by 1,000 r square comes out to be 1:10, right? So the correct answer is option D. Okay. Hope it's clear to everyone. If you understand, just write +1 in the chat box. Okay. Very good. Awesome. I'm assuming that we know that for a sphere, the volume formula is 4 by 3 pi r square pi r cube. We know this from our childhood. And the surface area is 4 pi r square. So that is why 4 pi r square, because we are writing the area here. Okay. Clear to everyone? Yes. 10th class mensuration. Absolutely. So everybody, so we got this. Answer is option D. Now we move on to the next topic, which we call as the excess pressure or additional pressure inside a water drop or any liquid drop or a soap bubble or any bubble. Okay. So why this happens, again, the property of surface tension is the reason. So what happens, guys, here? Due to the property of surface tension, a drop or a bubble, it tries to contract, obviously tries to reduce its surface area. So it compresses the matter which is inside. Because of that, there is an additional pressure which gets created inside. So always and always in a spherical liquid drop or a bubble, the interior pressure will be always more than the exterior pressure. Means if you look at this case, Pi will be greater than Po. Here also, Pi will be greater than Po. In other words or simpler words, if we look at any surface, do you guys understand concave and convex? Do you people understand the word terminology concave and convex? So if I'm looking at this side, if I'm looking at it from this side, this is concave or convex? Cave is being formed, cave is being formed, so concave. Okay, so remember, whenever we do this, this is concave side, this is convex side. So where do you think pressure will always be more? On concave side, the pressure will always be more. Remember that, because drop and balloon shapes or bubble shapes will always have the concave side inside. Okay, just a common sense to remember it. Point from something from the logical understanding of it. Okay, so let's find out the expression. The derivation is not important, but still we are doing it. They will not even ask you in your school examination the derivation, but the final expression is very important, not just from the school examination point of view, for your JEE point of view also. So there are two types of objects that you are trying to find the excess pressure for. One is a drop, liquid drop. Second one is the bubble. Okay, so drop has one surface, bubble has two surfaces. So whatever expression will come for the drop, bubble will have the expression double of that. Okay, so see how we do it. Okay, quick feedback. Is my video lagging? Is there a lag in my video? Some people are saying yes, some people are saying no. Okay, so what I'll do, I will rejoin the session once. Okay. Quick feedback. Any improvements? Okay, but yeah, all right, perfectly fine. Good, awesome, thank you. So we're switching off the chart so that we all focus here. What does it say? On the left hand side, you have a bubble. Sorry, it's a liquid drop. First, we're talking about a liquid drop here. Yeah, so we're talking about liquid drop. So this is basically a liquid drop whose radius is r. Initial internal pressure is pi, external pressure is po. And say due to some means, because of internal pressure, its pressure is further increased. The internal pressure is increased by dp, small amount, and the radius also sees an increment of dr. Okay, so obviously there has to be some external agent which is doing this and doing some work. So whatever is the work which is done by this excess pressure inside the drop, we can say that the force must have been applied and dr amount of length has been increased here. So simply force into dr. Force can be written as pressure into area, right? So pressure is p, area is the surface area of interior side maybe, and dr is the amount of change in the radius. Okay, so that pressure is p. This is basically the surface area 4 pi r square into dr. This is the amount of work done. We can also call it a small dw amount of work done, doesn't matter. Okay, guys. The increment in the area due to this excess pressure, if you look at it, whatever is the final area minus the initial area. So earlier the radius was r, so surface area was 4 pi r square. Now the area has become 4 pi r plus dr the square, because the radius has increased, right, everyone? So because the radius has increased, there is an increment in the surface area, and there is an increment in the surface energy also, by the way. So when we open up this square, it is r plus dr the whole square, r square plus dr square plus 2r dr. So you can see that this 4 pi r square and 4 pi r square cancels when I multiply this 4 pi inside. 4 pi dr square plus 8 pi r dr. In this expression, this dr square is a very negligible term. Now, why it is negligible term is because we know that dr is very, this is a value which is almost tending to 0. That means even if you consider, say, 0.001 is the value of dr, just an example, you will realize that if you square this value, that value will become, if this is 10 to the power minus 3, that value will be 10 to the power minus 6, which is further very small. So that is why if there is a term of dr square, dr cube, dr to the power 4 in whatever in calculus, you will always be neglecting it further. Okay, everyone? So what we are doing here, we are going to neglect this term. Okay, this is a very small term, so neglect it. Only effective part left is 8 pi r dr. So that is the change in the area. Okay? If I multiply this change in the area with the surface tension, I'm going to get the value of the amount of potential energy increased. How much amount of increment in the potential energy or surface energy is there? So surface area multiplied by the surface tension. So S into 8 pi r dr. Can I say that whatever was the work which was done here, this work done should be equal to the increment in the surface energy, right? Whatever increment has happened because of the additional change in the pressure. So we will equate this equation number 1 and equation number 3. Okay? So when we talk about equation number 1 and equation number 3, okay, we see that the value of work done, which was P into 4 pi r square into dr into S into 8 pi r dr. So we have just written it so smartly that we can cancel out certain things and see how this happens here now. You can see that 4 pi r is getting cancelled with 4 pi r, dr getting cancelled with dr. What you're left with? On the left hand side, you're only left with this r and p, and on the right hand side, you're left with this 2s. So what exactly is this pressure that you're getting? Is basically the excess pressure or the additional pressure. We could have started off by saying that this is the pressure difference also. At times you might find it written as the pressure difference because of which this is happening. So you can write delta p as well. Okay, what is important for us to understand? That this is the excess pressure. Excess means additional pressure. And if you look at this diagram, the additional pressure, delta P, is basically internal pressure minus the external pressure. Always the internal pressure will be more in comparison to the external pressure. So we can say it is P in minus P out. Now, again, as I said, what is not important is the derivation. What is important is the final expression. 2S by R is the excess pressure inside a liquid drop. Okay, it is inside a liquid drop. Okay, when we say air bubble, this air bubble inside a liquid. You know that there are air bubbles which are formed inside water, so they only have one surface where air is available. On the other side, water is there, so there is only one surface to them. So whenever there is only one surface available, the excess pressure value, internal pressure minus external pressure, is going to be 2S by R. Okay, and again, they're writing the same thing, that concave side is always on excess pressure comparative to the convex side. Okay, so the takeaway is that you have to remember this. Excess pressure is 2S by R, where S is the surface tension, R is the radius of that bubble, so not bubble but the drop, and delta P is the excess pressure there. Okay, so everyone, if this is 2S by R, excess pressure in the drop, how much are we expecting the excess pressure in a bubble? In a soap bubble, it's going to be double this value. We will do the derivation of that also, but please remember that value is going to be double because it will have two surfaces, so that value will come out to be 4S by R. Yes. So let's see how that comes. Everything will be changed. Bubble will double, exactly. Yes, you can say that. But not air bubble, soap bubble. Air bubble is formed only inside a liquid. Okay. Soap bubble is what forms in air. So soap bubble will have two surfaces which tries to reduce the surface area of the bubble. So again, if we calculate the work done, that value will come out to be, the force multiplied by the change in the radius. Okay, just a second. So delta P into area is the value of the force multiplied by dr. Okay. So note your derivation. मत नोट करो, क्लास के बाद नोट कर लेना. Only final expression is important as of now. Okay, yeah. So guys, please do not note down the derivation during the class. I've said this like a number of times. In fact, you don't need to do the derivation during the class itself. Only and only understand the derivation always. Okay. So here, what we are seeing, the work done has to be the excess pressure into the area into the R value. This remains the same thing here, but things will change when we speak about the surface energy. So when we talk about the change in area, obviously there are two surfaces whose areas are changing. The two times the similar thing happening here: 4 pi r plus r dr the square. You square that value, multiply 4 pi inside. You see 4 pi r square getting cancelled. This dr square will be neglected. So when we are neglecting this part, okay. So what you'll be left with is 2 times 8 pi r dr, or simply 16 pi r dr. That's going to be the total change in the area. Multiply that by the surface tension. 16 pi r dr into S becomes the potential energy. So equate equation number 1 and 3. What we get is excess pressure multiplied by 4 pi r dr into 4 pi r square into dr into surface tension 16 written as 4 into 4 pi r into dr. Again, we are writing it so that we can take some pulse of cancellations here. Okay, so dr also gets cancelled. You're left with 4s and here r. This comes down. So you have final expression of delta p. Okay, why am I writing it as delta p? Because that is what tells us excess pressure. Pressure in minus pressure out. Okay. So yeah, please note down this expression. Delta p is going to be the excess pressure. Okay, everyone. So this is the biggest takeaway. The two expressions. Expression came out to be double when we are speaking about not an air bubble but a soap bubble. Cool. Everyone is fine. So everyone has noted down the two expressions. Remember the difference. The difference between air bubble or liquid drop with a soap bubble. Okay, valid only for a soap bubble which has two surfaces. Okay. Okay. Absolutely. Yes. So let's have a look at the examples here. First one is a GMA 2018 question. They say that a small soap bubble of radius 4 cm is trapped inside another bubble of radius 6 cm. Okay, so we have this bigger bubble which has another bubble. This inside bubble has radius 4 cm. The outer one has 6 cm radius. Okay, and what it says, let P2 be the pressure inside the inner bubble. That means when we write the pressure, this is P2, and P0 be the pressure outside the outer bubble. That means this is PO or P0. Okay, P2 is inside the interiormost surface, and P0 is the pressure outside both for the entire system. Okay, just a minute, guys. So we have to find out the radius of some another bubble which has the same pressure difference P2 minus PO. So here we have two bubbles. We are talking about finding the radius of that bubble which has the same pressure difference P2 minus PO. Okay, so what I'm going to do, guys, I am going to say that maybe some pressure P1 exists here. Okay. Out of P2 and P1, which pressure should be more? Out of P2 and P1, which pressure should be more? Thank you. And out of P1 and P0 or P1 and P0, which pressure will be more? P1 will be more. Absolutely right. So can I say that when I write for outer bubble, I can say P1 minus P0 should be equal to 4s by R1 or R2, which is basically 4s by 6. That radius is 6 centimeters, correct? And if I write for interior one, it is P2 minus P1, which is going to be 4s by R1 because it is a soap bubble. So both will be having the same formula, 4s by R, but the radius is different. Do you guys get it, all of you? So far, so good. Because I want the value of P2 minus P0. What should I do with these two equations? What should I do with these two equations? If I add these two, will I get some cancellations? Right? You see that P1 gets cancelled. That's what we needed. Great. So P2 minus P0 on adding these two comes out to be 4s by 4 plus 4s by 6. Everyone is with me on this? So P2 comes out to be P0 plus 4s by 4 plus 4s by 6. Do we have the value of surface tension? No, we don't have. We don't have. We don't even need. Can I say that I want a single bubble? I want a single bubble which will have the same pressure difference. Can I say that is going to be 4s by some r value? This is what I want. 4s by r. This r is what I'm interested in finding. So what will I do? I will take this equation A and I will take this equation B and I will equate these two. So 4s by 4 plus 4s by 6 will be equal to 4s by r. Can you people solve and find out the value of r for me quickly? 1 by 4 plus 1 by 6 equal to 1 by r. Jaldi se. So r comes out to be 4 into 6 upon 4 plus 6. Right? So that is 24 by 10. Everyone is getting 2.4 centimeters. That's our answer. And that's the JEE 2018 question. Easy, doable. This was doable. If you know the concept right, the question is definitely not difficult. It is not like straightforward easy, but it is definitely doable. Okay? So we have this. Answer is option B. Okay. Sir, 4s by r, how I not understand? It is an air bubble that you're talking. Sorry, soap bubble that you're talking about. Harshita? फॉर्मूला क्यों लगाया या फिर यहाँ पे 4s by r क्यों लिखा? Is that the doubt? What is it? Question में बोला कि ये जो दो बबल वाली सिचुएशन है ना, यहाँ दो बबल्स हैं, राइट? हेलो, you want to replace the two bubbles by a single bubble, and that single bubble should have the same pressure difference. एक ही बबल में अंदर P0 प्रेशर होना चाहिए, अंदर P2 प्रेशर होना चाहिए और बाहर P0 प्रेशर होना चाहिए. तो उसका रेडियस कितना होना चाहिए वो पूछा है. तो ये लिखा है. Okay. I'm not discussing derivation now. Abhinav, whatever you want to, if you want to equate multiple equations, you do that. You try that. Final equation is important. Okay. Sir, is it practically possible that one bubble is inside the other bubble? I don't know. I've never done that, but I don't know the practicalities of it. So surface tension will always be going to be in questions where needed. Yes, surface tension will be given in the question, or they will be asking the value of surface tension in the question. Okay. Either it will be given or it will be asked. Okay. Cool. Chalo, question for all of you guys. Yes. इन दोनों के लिए लिख रहा हूँ ना, तो ये कौन सा वाला स्फीयर हुआ, बाहर वाला ना, इट्स अज्यूम्ड। अभी अभी समझाया क्वेश्चन में बोला है द रेडियस ऑफ अनदर बबल विद प्रेशर डिफरेंस P2 minus P0, so there is another bubble which will have only one bubble has the same pressure difference P2 and P0, so find the radius of that bubble. That's what question has asked us to find out. Now you understand? Mhm. As the surface energy increases, the surface area increases, or as surface area increases, surface energy increases. That's all. Correct. Okay. ठीक है everyone? अरे यार, I'm not unmuting in between, guys. You know that I don't do that. Please note down your doubts. You can ask me at the end of the class. I'm not doing that. Okay? Please note down your doubts. You can ask them to the class teachers also, or you can ask me at the end of the class. I never say no to the doubts, but during the class I will not take. Okay? Yes. Ask me as many as you want at the end of the class. Just note down the slide number. Just note down your doubt. That's it. Okay? Chalo, everybody. If you think you cannot, your doubt is so crucial that you cannot wait, you can ask with the class teachers also. There's no harm in that. Okay? Everybody, let's move on to solve the question. Sometimes when we solve the questions, also concepts get clear, right? So this one, again, another JEE main question for all of you guys to try. Pressure inside two soap bubbles are given to us. 1.01 and 1.02 atmosphere. The ratio of their volumes are going to be how much? So basically, there are two soap bubbles. So there are two soap bubbles. Okay? This is soap bubble number 1, soap bubble number 2. P inside, P outside. P inside dash minus P outside. Okay? So the inside pressure, okay, this is Pi and this is Pi dash given to us. P outside is the atmospheric pressure, which we all know is 1 atmosphere. Okay? So if the radius of this one is R1 and if the radius of this one is R2, question is asking us to find out the ratio of their volumes, volume 1 to volume 2, which is going to be R1 cube by R2 cube. So I've kind of given you almost every coordinate that you need to know in the question. Now I'll give you 90 seconds and the time starts in 3, 2 and 1. So okay guys, okay, let's see. Yeah, this was supposed to be done. Should have been easier for all of you guys to try. So P in is given, P out is, I have given you this value, though we already know this 1 atmosphere that pressure is. So P in is 1.01 minus 1, so 0.01 is 4T by R1. Okay, similarly the other one will become 0.02 as 4T by R2. So have a look at this. 0.01 is 4T by R1, 0.02 is 4T by R2. Take the ratio simply. So R2 by R1 comes out to be half, and we need the value of the ratio of the volumes, which is going to be R1 by R2 ka cube. So R1 by R2 is 2 is to 1. That means 8 is to 1 is the correct answer. Make sense, everyone? Okay. Okay. Sure. One more for all of you guys. Surface tension is, unless it is given, you will assume that they are basically made up of same soap film. So definitely surface tension will be same. Unless they are mentioning the value of surface tension, you will obviously consider it to be the same. Okay. Next one. The excess pressure inside the first soap bubble is 3 times that which is, okay, the excess pressure inside the first soap bubble is 3 times the excess pressure for the second soap bubble. The ratio of the volume of the first to the second one. Volume of 1 to volume of 2. So again, there are two soap bubbles which are being compared. The excess pressure value for the first one is 3 times the excess pressure value of the second one. Find out the ratio of the volume of the soap bubbles. V1 to V2. Giving you 2 minutes for this one, and the time starts in 3, 2, and 1. Come on, V2. Forty-five seconds remaining. Last 10 seconds, all of you. Okay, and the time is up. Much better, much better. Okay, nice. So again, kind of straightforward for all of us. If you look at the excess pressure formula, we know that is for a soap bubble, it's going to be 4S by R1. That is going to be 3 times 4S by R2. So we can see that R1 by R2 is going to be 1 by 3. So V1 by V2, which is going to be R1 by R2, the whole cube. So that's going to be 1 by 3 cube. So 1 by 27. That's going to be our answer. Okay, so this was easy for most of us. Good to know that. Sure, let's move on to the last topic of the day and of fluid mechanics also, called as the angle of contact and property of capillary action, or called as capillarity. So what exactly is capillary action, first of all? If we take, first of all, what is a capillary tube? There is something called as a capillary tube that you find in chemistry labs or at times in physics labs also. What is so special about capillary tube? Capillary tube is like a straw. It's like a straw, the one that we use to sip liquid. But it is a special type of straw whose radius, interior radius, is very small. Okay, it's so small that it is of the order of millimeters. Okay, so what happens with a capillary? That when we dip a capillary in the liquid, okay, so maybe there is some liquid which is filled here, and if we place a capillary inside it, a very thin capillary, so due to the property of surface tension, the liquid actually rises in the capillary tube naturally because of the property of surface tension, especially if there are adhesive forces between the glass of the capillary and the liquid. There is also a possibility that the liquid may fall down further in the capillary tube if the liquid and the glass surface, they have, it has very less adhesive property, or they are trying to go away from each other. This is what we call as the capillary action. And in day-to-day life, there is capillary action that we see. So guys, if by mistake, say you are sipping water and say water gets spilled on the floor, what do we do? What do we do? We put cloth over it. There is a special type of cloth, right? The wiping cloth. Have you guys ever noticed? If you have not, today, just notice the wiping cloth. You will find that wiping cloth is not synthetic. It is always cotton. It is always cotton. You will never take it as a silk cloth or any synthetic cloth. It has to have holes in it. I'll give you an experiment, another experiment that you guys can try. Take a take a bucket which is filled with some water and vertically take the cloth vertically. Just I'll give you the idea how you will do it. So take a handkerchief. Easiest would be take a handkerchief, take a bucket, and dip this part only. That means dip only the lower portion of it. Let only lower portion of it come in contact with water. After some time, you will find that water will come till this level also. Half of this or more than half of this will get wet. You can try this after the class itself. So why water rises by itself is the property of this cloth, which we call as the capillary action. This rising of the liquid, when there are small holes available due to the property of surface tension, is what we call as capillary tube or capillary action. Okay? Is the idea clear? Experiment आज दो experiment हो गए करने के लिए. Same happens with biscuit. Yes, tea and biscuit, sponge, anything which is basically porous will show the action called as capillary action. So we have 2 experiments to do from this. You guys can try doing this. Okay? मम्मी खुश हो जाएंगी कि फाइनली बेटा कपड़े धो रहा है अपने. Chalo, everyone, pay attention. So before we talk about the capillary action, we need to understand something called as the angle of contact. So when it is water and this cloth, the water rises. But there is a possibility that there is, this is basically called as the concept of wetting. The concept the cloth gets wet because of something which we call as the angle of contact. Let's try to understand what exactly is angle of contact. What is angle of contact is very simple. The angle of contact is basically the angle between tangent of the liquid surface, this is the tangent, and the point of contact on the solid surface. So if you draw a tangent here from the point of contact and try to measure this angle with the liquid surface, this angle is what we call as the angle of contact. Okay? This is basically the angle of contact. And it is also possible that there is a obtuse kind of angle being formed. Okay, so this is a typical example of water and glass. Okay, and this is a typical example of mercury and glass. Okay, so this dip that you are seeing in the liquid and the rise that you are seeing in this liquid is what we call as the meniscus. Okay, this is meniscus of the topmost surface that you are seeing here. So what happens, guys? If this angle of contact is an acute angle, then the liquid will try to wet the surface. It will try to get in touch with that surface, which happens with cloth and water. You might have seen this also especially during little winter time. If you go on morning walks ever, you will find there will be water drops on the leaves, those big leaves, right? That is again the property of the angle of contact, but that liquid drop is not trying to wet the leaf over there. So that is because the angle of contact is an obtuse angle. So if angle of contact is an acute angle, the liquid will wet the surface. It will try to stick to the surface. And this is the situation where adhesive forces are stronger. This is where adhesive forces are stronger. Liquid and glass are different materials. So if they're trying to get in touch with each other, that simply means that liquid is trying to get friendly with that surface. But if that is not trying to get, the liquid is not trying to wet the surface, in that case, it is basically the obtuse angle and adhesive forces are weaker. Yes, that is why mercury usually is the case where obtuse angles are formed. Okay? And I've already given you the idea what exactly is a capillary tube. So capillary tube especially will show these type of situation or possibilities. So what happens in a capillary tube? There's something called as capillary action that I explained it to you. So if it is water in a glass, that means if the capillary tube is made of glass and you dip that capillary tube made of glass in water, you will find naturally inside the tube water rising to a certain level. But if you do that same thing in mercury, again something that you can only do in physics lab because it is very difficult to have mercury available. So if you ever get a chance to do this capillary tube dipping in the mercury, you will see that mercury in the capillary will dip because mercury does not want to get wet with or rather it does not want to wet the surface of glass. It wants to repel that surface because it is forming obtuse angle. So the height by which the liquid rises or falls in the capillary tube is what we are interested in finding. Our objective is to find this value of height by which the liquid is rising or dipping. Formula will be same. It is only dependent upon the value of theta being acute or obtuse, more than 90 or less than 90. That's the same. Okay, everyone. So capillary action is the ability of the liquid to flow in narrow spaces without the assistance or even in the opposition of the external forces like gravity. So even if there is no gravity, the liquid will rise. In fact, this is happening against the gravity. Okay, everyone. So please specifically remember this is water glass system and this is mercury glass system, the typical one that we discuss in our syllabus. Okay. So let's try to find out the formula. Again, the formula derivation is not important. Final result is important. So say if we consider a capillary tube, this is the formula that we're trying to find out, and this is the meniscus which is formed. Okay. So what is happening here, guys? This is like the surface of the liquid or part of a spherical surface of the liquid which is being formed here. I want your attention on this, everyone. This is what I'm trying to say. If there would have been a, the air bubble which only has one surface. So this is the kind of situation it would have been into. Right? I'll draw this here for you. Okay, just to visualize this part. So if we talk about, they have drawn a different type of, they have taken the center of that imaginary sphere to be here. I'll just remove that so that it becomes easy for us to understand. This is that imaginary sphere. Okay, whose center is here. So sphere ka radius is capital R and small r is the radius of this capillary tube. Okay, the capillary tube ka radius is small r and the imaginary sphere which is formed on the top of that surface is what we are calling as capital R. So this right angle triangle which has been formed has this angle as theta, which is the angle of contact, by the way. Okay, so everyone, we want to find out, first of all, the pressure A and B. If we talk about this point is A and this point is B. Here I'm talking about. Can you people tell me where the pressure will be more, A or B? Where do you think the pressure should be more? On the concave side it will be more. So we know that pressure at A is greater than pressure at B. And what will be PA minus PB? Can I say that value is going to be 2S by R and capital R, by the way, capital R, not small r. Okay? So can I say PB is equal to PA minus 2S by R? Can we write it? Right? What is PA? Is it exposed to the atmosphere? So PA is nothing but atmospheric pressure. Everyone understands? Correct? So this is the expression written here. PB is PA minus 2S by R. Okay, everyone? Yes. So looking at this diagram once again, please pay attention, all of you. In this right angle triangle, okay, this angle is theta, this is capital R, this is small r, this is O, this is L, sorry, this is Q, this is L, and this is O. So what is OQ? OQ is capital R. And what is OQ? It is the radius of curvature of the liquid, the imaginary sphere that I was talking about. QL is the radius of the capillary tube itself. So this is the capillary tube, small r radius. S is the surface tension of the liquid. So what I'm going to do now, everyone, in this right angle triangle, I can say that cos theta is going to be small r by capital R. So capital R means the radius of curvature of the sphere is equal to the radius of the capillary tube divided by cos of theta. Okay? Why do I need this? Because I want my final expression, this capital R, to be in terms of small r, the capillary tube that I'm using. Okay. So if I know the surface tension value and if I know the radius of this, the capillary tube, I should be able to estimate how much liquid is going to rise in that tube. Is what my interest is. Okay, everyone. So see this. If we write the value of pressure at E now, okay, pressure at E obviously is going to increase by H rho G. So pressure at E is equal to pressure at B plus rho GH, and pressure at B which is now found here, P minus 2S by R. So you see this P minus 2S by R is written plus rho GH. Also, can I say that, everyone, at equilibrium, these 2 points D and E should have the same value of pressure? Let's see how many of you remember this property. The 2 points which belong to the same layer, they always have the same pressure in a liquid, right? Yes, yes, absolutely. Okay, so that's great. So PD right now, D is the point which is almost on the surface and it is exposed again to atmosphere. So PD is almost equal to the atmospheric pressure. Writing it here instead of PE, we are writing it as P equal to P minus 2S by R plus rho GH. Do we understand this equation, everyone? What have I done? I have written PE in terms of PD, or rather PD is also equal to P equal to the atmospheric pressure. Okay, so P gets cancelled. 2S by R is equal to rho GH. H comes out to be 2S by rho G capital R, but we don't want our expression in terms of capital R. We don't want our expression in terms of capital R. We want it in terms of the radius of the capillary tube. So when we replace R as small r by cos theta, this is the final expression, the very important expression here. The rise or fall of the liquid in the capillary tube. Okay. This is also valid for capillary fall. 2S cos theta by rho GR. S surface tension, theta contact angle, rho density of the liquid, G we already know, R is the radius of the capillary tube. Okay. So S is surface tension, will be given to you obviously in the question or will be asked in the such questions. Then we will have theta, that is contact angle. If contact angle is less than 90 degrees, liquid will rise. Okay. If contact angle is more than 90 degrees, the liquid will fall from common sense. Okay. The rho is liquid density and R is already explained here. Everyone is clear? Are we clear with it now? Can you remember the formula, everyone? Note it down, the formula. Is the derivation important? Is the derivation important? Actually not. The derivation is not important. But what is important is the final expression. Yes. Okay. Yes. For value 90 degree or more than that, the value will give you the negative value. That means the liquid is falling. Okay. Yes, everybody. Chalo. Let's have a look at some examples and a lot of questions for you people to solve. And somebody in between was saying, sir, question of the day. That will also come. Okay. So everyone, the question: water rises to a height of 10 centimeter in a glass capillary tube. If the area of cross section of the tube is reduced to 1/4 of the former value, then what is the height of the water now to which it is going to rise? So here already the value of height to which the liquid is for a given radius is given to us. So if I'm going to reduce the area to a by 4, we know that area of the tube when we are writing the surface area, cross section area is pi r square. So if area becomes 1 by 4, the radius will become r by 2. You can try that. Okay. You can try writing this in terms of r. Okay. Is it very obvious for everyone that if radius becomes half, area will become 1 by 4? Everyone understands this? No? Yes? Great. So can I say that height, okay, height has to be found. So looking at the formula, it is 2s cos theta by r rho g. So you can see that it is inversely proportional. H is inversely proportional to r. So if r is becoming half, the height should become double. The answer is going to be option A. That easily you can answer this question. Okay. Great. Awesome. बहुत बढ़िया. Sure. Questions for all of you guys to try now based on this formula only. H is inversely proportional to R. Yes, Mitra. Do you see this here? Sure. Switching off the chat so that you guys focus on the quiz. Question number 1 for all of you. The correct curve between the height or depression h of liquid in a capillary tube and its radius is going to be. So this is direct application of the formula. If you remember the formula, you'll be able to correlate the graphs also. Graph between h and r. R is the radius of the capillary tube, and we'll give you 45 seconds for this. And the time starts in 3, 2, and 1. Last 10. Okay. And the time is up. Good to see that decent number of people have answered it correctly. So I just now told you that h is inversely proportional to r. That means what? It is definitely not a straight line relation. Okay, so answer cannot be A, C, and D. Other way of looking at it is if r approaches 0, h approaches infinity. So if r becomes 0 here, h will go to infinity, or vice versa. Such graphs are called as hyperbola. Okay, so the correct answer to the question is B. Okay, sure. Now a numerical one from JEE Main 2020. So question says a capillary tube made up of glass of radius 0.15 millimeter is dipped vertically in a beaker filled with the methylene iodide. Okay, some liquid, I don't even remember anything about it. So CH3I maybe. So surface tension is 0.05 Newton per meter of that liquid. Density is given, and it rises in that capillary tube to a height h. It is observed that two tangents drawn from the liquid glass interface from the opposite side of the capillary make an angle of 60 degrees. So you can easily figure out the angle of contact here. Okay, so you have to find out the value of h, giving you the formula myself. It is 2s cos theta by r rho g. Okay, so surface tension is given, the density is given, small r is given. What else needed? Rho is given. You have to just figure out theta value. I'm going to give you all complete 2 minutes for this, and your time starts in 3, 2, and 1. Come on, guys. Just application of formula. Yes. Roughly 30 seconds more. Okay. Time's up. So what is going to be the contact angle? 60 or 30? Thank you. Yes. This is the contact angle. That is 30 degree. उसके बाद में से formula application. Okay. So 2s cos theta by r rho g, 2 into surface tension, cos 30 degree, root 3 by 2. R is 667. Sorry, density is 667 kg per meter cube. G value is 10. This is rho. This is G, and this is going to be, I will write it as either 15 into 10 to the power minus 5 or 0.15 into 10 to the power minus 3 meters. Okay, so simplify karna tha. That was the only task that you have to put efforts on. So 0.087 meters will come out to be the answer, which means 8.7 centimeters. 8.7 centimeters is the rising of this liquid. Okay, chalo everyone. The question of the day for all of you. Read the question. Question says that if m is the mass of water that rises in a capillary tube of radius r, then how much mass of water will rise in a capillary tube of radius 2r? Okay, so if the same liquid rises to a height of h and has m mass in a tube of radius r, if you double the radius of that capillary tube, how much mass do you think is going to rise? Okay, complete 2 minutes for this, and your time starts in 3, 2, and 1. Okay, last 10 seconds now. Come on, everyone. Let's see. Okay, okay. सबने सोचा होगा डायरेक्टली मास प्रोपोर्शनल टू एच है एंड एच प्रोपोर्शनल टू 1 बाय आर है, ऐसा कुछ कर लेते हैं. So when we write this m, this is density into pi r square into 2s cos theta by r rho g. So what do you see? Everything else, density is constant, surface tension constant, contact angle for same liquid and solid remains the same. So only r is the factor which is to be seen here. So comes out to be proportional to r. So mass is proportional to r. This is what you had to reach the conclusion to. Okay, now I can see that because majority of you directly saw that sir has highlighted h and h is inversely proportional to r. So if height becomes double, mass should be halved, right? And that's why many people have answered it as B. But the correct answer is if radius doubles, the mass which is rising up will also double. That means answer is going to be option D. Okay. For all of you. Okay. So let's have a look at the leaderboard. We have completed like 5-6 minutes before the session time. That's really commendable. Congratulations to people who have solved 7 or 8 questions today correctly, and those who are here in the leaderboard, well done. Those who are not here but still have solved a good number of questions, you guys are no less. You guys equally are awesome. Okay, and here we go. This brings us by the way to the end of fluid mechanics. So fluid mechanics ends here. We will be entering into thermodynamics. Thermal physics will be started, and we'll leave SHM and waves for the end. Okay. And I think now we'll meet after Diwali. So this is welcoming the winter breaks. We don't get much of a break though, right everyone? सब एक साथ ले लो आज तो कुछ भी नहीं छोड़ा. This one. Happy New Year पे करेंगे हम लोग, Christmas पे करेंगे. ठीक है. So this is officially the end of the discussion of the class today. Class teachers, if you're done explaining your doubts to the students which have been asked to you, you can exit the session. Those students who want to have dinner and want to get back to their routine, they can also exit the class. बाकी की जनता is here. Yes. अरे किसने बोला भाई we cannot find surface tension? मैंने एक बार भी ऐसा बोला क्या? In this slide, before 50th slide. He's having khichdi today, by the way, everyone. He's having khichdi. In this question, you're saying, if I say, I don't remember saying that we can't find surface tension. We can find surface tension all the time. Because none of the question was asked us to find out. That's why. Okay. Oh. Okay, fine. Yeah. Yes, Apurva. ड्रॉप में और एयर बबल जो कि पानी के अंदर बनता है उसमें एक ही तरफ हवा है, एक ही तरफ एयर है, लेकिन जो सोप बबल बनता है उसमें अंदर भी हवा है, बाहर भी हवा है. दैट इज व्हाई. हाँ, सरफेस फोर्स उससे परपेंडिकुलर होता है उस सरफेस से. हाँ, ठीक है. ओके, बाय बाय. some people are asking sir why it is proportional to m, why m is proportional to r. ना surface tension is the property of the liquid. चाहे ये बॉटल भर के वाटर लो या फिर टैंक भर के वाटर लो, surface tension को लेने देते हैं unless you are mixing something in dirty in the liquid. Okay, so yeah, this is quite simple to understand that why this is happening here. If we try to look at the constant here, density is constant. Okay, whoever I will rejoin. Now is it fine? Am I audible properly? Sure, good. Okay. So some people were having doubt that why this mass expression became proportional to r. So we know that mass is density into volume. In the capillary, when the liquid is rising, say it is rising in the form of a cylinder, right? So I can say that the volume of the cylinder is going to be pi r square into h. So pi r square h is written. H ka expression we already know. So 2s cos theta by r rho g. So this density got cancelled. G is a constant, pi is a constant, surface tension is a constant, and angle of contact is a constant for a given combination. So can I say that it is r square divided by r, which is eventually r only proportionality wise? Those who had doubt, is it clear to everyone? The last question. Okay. Yes, Ansh. तो कुछ गड़बड़ हुई. All the approaches are correct as long as they are mathematically correct. As long as it is air bubble, as long as it is air bubble, it will have two surfaces. If it has liquid drop, or sorry, as long as it is soap bubble, it will have two surfaces. If there will be a liquid drop or an air bubble inside liquid, they will only have one surface. ये याद रखना है. Okay. आने दो, आ भी गए तो क्या प्रॉब्लम होगी? फॉर्मूला तो वही रहेगा, नंबर ऑफ सर्फेसेस तो नहीं रहेंगे अभी भी. ठीक है, सिर्फ एरिया चेंज हो जाएगा, सरफेस एरिया. तो सरफेस एरिया तो हमें इंसुलेशन से मालूम है कैसे लिखना है ना. ओके. सर ये meniscus का क्रॉस सेक्शन भी पैराबोलिक होगा like in rotation of the liquid. So actually the meniscus is spherical, Alik. It's not parabolic. It's spherical. Diksha, atmospheric pressure in slide number 52 you are saying, right? Slide number 52 पे तो ऐसा कुछ नहीं, हाँ ये वाला एटमॉस्फेरिक प्रेशर का वैल्यू ही एटमॉस्फेरिक प्रेशर 1 एटमॉस्फेयर होता है दीक्षा, एटमॉस्फेरिक प्रेशर का वैल्यू ही 1 एटमॉस्फेयर होता है, और ऑब्वियसली सोप बबल के बाहर एटमॉस्फेरिक गैसेस है ना, तो दे विल क्रिएट अ प्रेशर ऑफ 1 एटमॉस्फेयर। और क्यों एटमॉस्फेयर में लिया, न्यूटन पर मीटर स्क्वायर में क्यों लिया, क्योंकि ऑलरेडी ये प्रेशर एटमॉस्फेयर में दिया हुआ है, दैट्स व्हाई। ओके बाय राधिया, यस अमन, गुड इवनिंग बच्चा। ये वाला ये वाला कौन सा भी, ये क्वेश्चन ने बोला कि यहाँ भी 2 एयर बबल्स हैं, सॉरी 2 बबल्स हैं, है ना, तो देयर आर 3 प्रेशर जोन्स, एक है P2, एक है P1 और एक है P0, है ना। तो एक ऐसा सिंगल सोप बबल का रेडियस पता लगाओ, या एक ऐसा सोप बबल ढूंढो जिसमें इंटरनल प्रेशर P2 हो और आउटसाइड प्रेशर P0, एक ही सोप बबल, यहाँ 2 सोप बबल है ना, रेडियस ऑफ अनदर बबल विद प्रेशर डिफरेंस P2 - P0, तो ये वो सोप बबल हो सकता है जिसका रेडियस R है, हमें नहीं मालूम कितना है, और जो भी होगा उसका प्रेशर डिफरेंस 4s/r होना चाहिए ना, तो वो ठीक है, इसलिए ए और बी को इक्वेट कर दिया हमने। अरे हाँ यार वो एक चीज है, वो मैं नेक्स्ट टाइम करवा दूंगा, डोंट वरी। छोटा सा टॉपिक है, रेनॉल्ड्स नंबर का एक फॉर्मूला है जिससे मालूम पड़ता है कि जो फ्लो ऑफ लिक्विड है वो टर्बुलेंट है या फिर स्ट्रीमलाइन है, ठीक है, तो वो चीज हाँ डेफिनेटली मुझे याद दिलाना नेक्स्ट टाइम जब भी क्लास होगी, आज मैं सोचा था करेंगे पर दिमाग से निकल गया, ठीक है, बहुत छोटा सा टॉपिक है, इट विल टेक 5 मिनट्स ऑफ आवर्स, विल डू इट, एक फॉर्मूला बस, ठीक है मैम, ओके। यस विहान, गुड इवनिंग, बिल्कुल आ रही है, बताओ। मैं ठीक हूँ लेकिन लगता है तुम्हारा इंटरनेट आज थोड़ा वीक है। ओके ओके, व्हाई इज एवरीवन विशिंग अर्ली दिवाली, बिकॉज़ नेक्स्ट वीक यू डू नॉट हैव एनी क्लास ऑफ फिजिक्स केमिस्ट्री और मैथ्स। सर एक बार दिवाली के नाम पे गा दो, क्या गाऊं भाई, मैं थोड़ी सिंगर हूं। यस समर बेटा, यस यू आर, गुड, वेरी नाइस। बताओ बताओ, फिट एंड फाइन एज ऑलवेज, आई नो करेक्ट, हाउ यू बीन, ओह माय गॉड, नाउ you go, it was not being moved, no double Bible right, okay okay, एक मिनट, क्या यार मानो, विच स्लाइड समझ बेटा, स्लाइड नंबर 10, ऐसी शायरी जाके तुम लोग ना इंस्टाग्राम पे करो, वेदांतु प्लेटफॉर्म पे नहीं, हाँ यस टेल मी। It is. So that is why imaginary line you draw anywhere. It's an imaginary line. In all possible directions, the situation exists. Yes. And that is why surface tension is basically it's a tensor quantity. Because in every possible direction you will find its value, but it is still not a vector quantity. So that is why it is a tensor quantity. But good observation, yes. So it will be in all possible ways. You draw this line, black wala line, you will find line perpendicular to that will experience the force. Means it's like if ever the surface of a drum will break or rupture by itself, this is how it is going to rupture because of the forces acting on both the sides. So that's how it will rupture. If ever. Yes. Exactly. So that is because of the force generated due to surface tension. Why cannot we draw a line horizontal? You can draw a line horizontal or any which way. This is not a vertical diagram, this is the top view. 47, yeah. Mm-hmm. Can't say, can't comment. Maybe in laboratory conditions, yes. Means technically it is possible. Practically will be very difficult. But with the help of certain equipments, we might. So without breaking the outer bubble, if we are able to supply that soap film inside, then maybe we can. Yes. I have never seen it, never seen any video also. That's why I said I do not know practically it is possible or not. But technically it is possible. That there is no denying on that. It is possible to have it. Theoretically, yes, बिल्कुल possible है. So it's a gentle equilibrium which is being formed over there. As long as the amount of surface tension which is generated on the surface is able to maintain the difference of the pressure which is required for that surface to sustain, till that time the surface will not rupture, and obviously it has to do something with the elastic property of that liquid surface also. So if that elasticity nature is being tested, or if that excess pressure creates the force on the surface so much that it is able to create breaking of the hydrogen bonds, considering that there are liquid or whatever kind of bonds which are formed, if you are able to separate the two molecules at any place on the surface of that film, you'll be able to rupture the film, not just for bubble, for any planar surface also, any soap film we can talk about. It's eventually what is happening, eventually there are molecules which are bonded together, right, and there are weak van der Waals forces by which they are bonded maybe. So if by any means you are, and surface tension is trying to take the molecules away from each other. So if that surface tension is strong enough, or if you are increasing the surface energy so much, there will definitely come a point where the force generated because of surface tension will be able to overcome the force acting between the molecules, and then the film or the surface is going to break down. It's formed as I'm not able to understand what exactly. So when we take a straw and when we dip that straw inside the soap solution, you take it out and you try to blow air in it. So it tries to create a bubble kind of surface there, and from there something happens because it's able to convert itself into a bubble. So basically, by blowing the air, we are ensuring that the concave side has more pressure than the pressure outside. We're trying to make sure that excess pressure situation is being created. So as it expands, there eventually will come a stage where it takes the entire shape of the sphere. I do not know the exact mechanics of it, and I'm not able to comment on it practically. But technically, excess pressure situation is satisfied. There has to be sufficient surface tension, Vihan. Then only, if you just dip your straw in water and try to blow, bubble will not be formed. But if you have soap solution will have that certain possibility of having that surface tension, because of which the soap molecules will stick to each other to create a soap film. Come again? We can again. Then we are getting in the domain of chemistry. Definitely, there are multiple fluids possible for which surface tension exists in all the fluids. It is just that to make it visible to us, the experiments are conducted with the help of soap films. But definitely, there is a possibility to mix soap in some other liquid. The possibility of creation of soap bubble is there. Okay. So first of all, we have technically found that part. Mathematically, we have seen why this is happening. Secondly, the surface tension is always going to be tangential to a given surface. Look at this one. So what is happening to the concave side is the force which is trying to act on any of its imaginary ring. It is trying to bind it with the other half of this spherical's body. Means if this is a soap bubble, because of this force on one half or one hemisphere of this soap bubble, this force is basically trying to connect the other hemispherical part of this bubble. So the surface tension is trying to create as minimum area possible for the interior surface as possible. So in this case, we just now spoke about, in fact, during that part only, this explanation came as well. The drop of the bubble will try to contract and compress the interior matter in this process. When you're applying the force tangentially, you're trying to create a force on the interior molecules. So in that, you're basically trying to compress the liquid material. Say if you take it as an example of a drop. In drop, when you're taking the shape of a spherical body, you're trying to create the force from outside to the interior molecules. We know that in the beginning itself when we spoke about the surface tension property, it comes because of the difference of the force experienced by the bulk molecule and the surface molecule. So if we speak about, say liquid drop, the liquid drop has surface molecules which are overall experiencing interior force. Can we say that? So imagine for a drop, interior force coming in all possible directions. Can we say that it will result in an added pressure inside comparative to outside? Because of that, the pressure inside the spherical zone will be more comparative to the outer pressure. Yeah. No problem. Can we calculate the time? If we look at why the soap bubble is going to rupture, first of all, if it is going to stay in the present state where it is, especially maintaining the pressure. So when we will be now moving on to thermodynamics, we will understand the correlation between temperature and pressure. Okay. So if you are able to maintain the thermodynamic condition to be same, and your air bubble is also not coming in contact with any other solid surface, the soap bubble will maintain its shape forever or for an infinite period of time. But practically, as the soap bubble is formed, if the temperature gets changed, the pressure also gets changed. Because of that, the rupturing will happen. So if we find a correlation, or if we are given with the correlation, how the pressure is changing and how the temperature is changing with time, then we will be able to find out when that certain threshold value is being crossed, so that there is possibility of breaking the surface. But it will be a very complicated question to try, because it will be dependent on multiple factors. So many observations and so many assumptions will be involved, at least at the J level. Okay. Okay, Samadhita, Vihan is no problem. But Vihan, on the other hand, is asking, sir, can you now unmute me? So we'll speak some other time. Take care. Bye bye. Good night. Yes, Vihan, we have limited time. बिल्कुल आ रही है. Start speaking. बोलो बोलो बोलो. हम्म, हम्म, हम्म. पहले ये पता लगाया कि अच्छा, if the coefficient of friction is given, ब्लॉक और टेबल के बीच में दिया है. सो एक बुलेट है, एक ब्लॉक है, और यहाँ पे कोएफिशिएंट ऑफ फ्रिक्शन दिया हुआ है. और क्या पूछा है, क्या पता लगाने बोला? ओके 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 ओके. तो इसकी जो भी इनिशियल स्पीड है, वो जो भी मोमेंटम है, मान लेते हैं कि जितना भी ट्रैवल करेगा, फाइनली उतना मोमेंटम ये इसको ट्रांसफर करेगा. ठीक है, लॉ ऑफ कंजर्वेशन ऑफ मोमेंटम से. तो मैं बोल सकता हूँ कि m into u will be equal to m plus small m into v. तो मान लेते हैं दिस इज इंस्टेंटली हैपनिंग. बहुत कम टाइम लगता है बुलेट को पेनिट्रेट करके अंदर आके रुकने के लिए. तो बहुत कम टाइम ऐसा हो गया. मैं ये वेलोसिटी पता लगा देता हूँ. ठीक है, तो इनफैक्ट एक क्वेश्चन पूछा है कि कितना मूव करेगा या कितनी देर बाद मूव करेगा. कितना मूव करेगा. ठीक है, गुड. सो वी गेट द वैल्यू ऑफ दिस वेलोसिटी, है ना. तो हमें वेलोसिटी मिल जाएगी, और अगर वेलोसिटी को 0 होना है तो फाइनल वेलोसिटी, इनिशियल वेलोसिटी v होगी of the combined mass, and v final is going to become 0. The rate of retardation is going to be mu into g. Mu का वैल्यू दिया हुआ है, g का वैल्यू दिया हुआ है. तो कितना डिस्टेंस मूव करना है, that is going to be v final square, v initial square, assuming that this value will come out to be constant, which will come out to be constant क्योंकि mu का वैल्यू वहां से दिया हुआ होगा. Okay, so v final square is equal to v initial square plus 2, in fact माइनस लिख देना क्योंकि रिटार्डेशन हो रहा है, minus 2 into a into s. तो s का वैल्यू निकल आएगा, ये वैल्यू 0 हो जाएगी. बस v initial का वैल्यू v है, वो यहां से मिल जाएगा. ये वैल्यू दी हुई है, ये वैल्यू दी हुई है, तो m plus m से डिवाइड करोगे तो v का वैल्यू आ गया, which is basically the initial velocity. फाइनल 0. तो सिर्फ s का वैल्यू नहीं पता है, बाकी सब पता है. सिंपल. अभी भी आते हैं. जी का एग्जाम बच्चों के लिए तो बनाए देने के लिए, तो बच्चे क्लास नहीं करेंगे तो फिर फायदा क्या है जी एग्जाम का, राइट? उन्हें किसी को किसी दूसरे प्लैनेट के लोगों को ये थोड़ी बताना है कि हम ऐसा एग्जाम कंडक्ट करते हैं, किसी से सॉल्व नहीं होता ही है, क्वेश्चन तो वही बात है ना? एंजॉय करो, चिल मारो, रिलैक्स करो। मतलब देखो पूरे एक साल में एक ही वेकेशन आती है, और 11th में आती है तो एंजॉय कर लो, 12th में एंजॉय नहीं कर पाओगे, क्योंकि 12th में चल रही होगी टेंशन, जेईई मेन आ गया। अभी जो तुम्हारे 12th स्टैंडर्ड के स्टूडेंट्स हैं ना, तुम्हारे सीनियर्स, उनके दिमाग में चल रहा है कि यार मैं इस टाइम पे मेरा बैकलॉग कैसे कवर करूँ, 11th कैसे रिवाइज करूँ, उनके दिमाग में ये चल रहा है। तो तुम्हें अभी वो टेंशन नहीं है, तो जितना हो सके एंजॉय कर लो, थोड़ा बहुत मन करता है पढ़ने का तो पढ़ लो, कुछ लगता है सिग्निफिकेंट है जो करना चाहिए तो कर लेना, बाकी अदरवाइज डेफिनेटली स्पेंड टाइम विद योर फैमिली without any guilt to everyone, without any guilt. Do not take any guilt if you do not study much in the Diwali week. Okay, you said this a number of times. Sure. All good, yeah, all good. Everything is fine. हाँ यार मैं बैंगलोर गया नहीं लास्ट वीक, इसलिए है ना, जब रिजल्ट था तब मैं गया था, हाँ फेलिसिटेशन था तब मैं नहीं गया, है ना। एक क्लब में भी टीचर्स ऑनलाइन पढ़ाते हैं, ऑफलाइन नहीं पढ़ाते, है ना। तो अगर मिलना मिलेंगे डेफिनेटली कभी लेके टेंशन ना सर। ओके चलो, yep, you too, bye bye. Sir, can at any point outer pressure have more pressure? Now, outer side will not have more pressure. Uh, yes, Nihal. Which question you're talking about? This one. This one. Tell. And a drop of water has only one surface outside it where we have air. Okay, but a drop only has air on one of the sides. Okay, but a soap bubble has air inside and outside. Okay, to remember it, this is how I always remember. The surfaces which are exposed to air are the one which we consider. Okay. Okay, everyone. So happy Diwali to all of you. Happy Diwali in advance. And as I said, do enjoy. Okay. Do not take any guilt if you are not studying much. Okay. Absolutely. I said try. I did not say don't. I said try. Okay. Yes, Pariti. Same here. अरे बिल्कुल कर सकते हो यार, देखो पढ़ना है तो पढ़ तो बिल्कुल सकते हो, नहीं पढ़ना है तो ऐसा मत सोचना कि मैंने दिवाली पे कुछ पढ़ा नहीं। तो अगर तुम्हें लगता है कि यू कैन स्टडी ड्यूरिंग दिस ब्रेक आल्सो, देन डू। बट नहीं पढ़ पाए तो गिल्ट मत लेना, बस दैट्स द ओनली थिंग आई कैन से। ओके, I always celebrate with my family. I try things for me, being with my parents, being with my family members around them is what Diwali is. You all know that I'm not a religious person. I don't believe in religion at all. But for me, Diwali is a bahana to be with my family, entire family, right? Yes, absolutely, I'm going to Kota. Okay, yes, absolutely. Okay. So this time, when I'm in Diwali and I'm in Kota, I will send videos on that Telegram group. Okay. Yeah. Okay, guys. So I guess time is almost up. Let's wrap it up without randomly getting disconnected. We'll see you all after Diwali. Have fun. Take care. Enjoy. Have a guilt-free Diwali. Enjoy to the fullest. And don't get crazy. Don't go crazy. Just stay in your senses. Okay. Have fun. Yeah. Chalo then, everyone. Bye bye. Hasta la vista. Sayonara. Signing off. See you all next time. Good night. Bye bye. Happy Diwali.